In this video lesson, let's work at a different example outside of that example that was given throughout the general lecture for comparing two population proportions. And so in this example, I will also be working as a problem that compares two population proportions. So let's get started by looking at the given information as following. And here I apologize for the very sketchy description of the two samples, but it should be descriptive enough. So from Newton University, we sampled 550 students from the university student population, and we found out that 140 of them are engineering major. And then in the same way, we sample 500 students from Gauss University, and in that sample from Gauss University, the sample of 500 students from that Gauss University, we found 100 of them are engineering majors. So throughout the two samples here, it looks like what we looked for mainly was the category being engineering majors, engineering major and engineering majors. And of course here I'm using the majors as a plural here, indicating that engineering itself, the engineering field, is a very large major. There could be civil engineering, there could be electrical engineering, there could be chemical engineering, a lot of different fields in engineering. So as long as you are one of the engineering majors, then you are in that count, you are in that proportion. And so now from that understanding, and this is even before I get into any of the question here, then we can define for ourselves the main population proportion here is to be, how about let's call that lowercase letter p to represent the proportion of engineering majors. So what we have now defined the proportion lowercase letter p here to represent the proportion of engineering majors. But this is just a general population proportion, the proportion of engineering majors. It can happen, this proportion can be found in Newton University, it can also be found in Gauss University, it can be found in any universities worldwide, as long as the university has a school of engineering. And so in our particular problem, let's have a look again at the wording in the problem. Then the description in our problem here describes the two samples from the two different schools. So one sample is from Newton University, and the other sample here is from Gauss University. So now that tells us that as we study this population proportion of engineering majors, we specifically would like to turn our attention to the two separate populations. We want to look for this population proportion in Newton University, and also we would like to look for this population proportion in Gauss University. So now at this point we understand that we have separated this proportion, this population proportion, into two separate populations. And so very similar to the explanation that was given in the example throughout the example that came along with the general lecture, then we can now start out by deciding our numerical labeling for each one of these two populations. So I can make my choice, and any viewer who works along with this example can also have your own choice of the numerical labeling. But I simply decide here that I call Newton University being population number 1, and Gauss University on the other hand is the population number 2. I don't personally know any of these two universities. So the reason I gave these labeling not because I favor Newton University better than Gauss University that led to having label 1 on here, but the reason I'm doing that simply because Newton University is described before Gauss University according to the data I'm given here. And so in that way, back on my writing board, once we have decided for ourselves the labeling convention, the numerical labeling here, then clearly I can now refer to Newton University as population number 1. And Gauss University, the student population there is regarded as population 2. And so now that specific population proportion of engineering majors, but in population 1, now we can refer to that as P1. And of course, obviously, at this point, we do not know the actual value for this true P. That population proportion of engineering majors, but in specifically population 2, we now refer to that as P2. And so anytime later on throughout the problem, if I need to refer back to any of these two populations here, I am going to refer to them as population 1 and population 2. And same way, P1 and P2. Once we have decided for ourselves the numerical labeling on these two populations, then the sample that was selected from Newton University, this is to have sample size as it said clearly here, 550 students sampled. We found 140 of them are engineering majors. So in that way, now obviously from population 1, each sample came out from population 1 was as large as 550 students. And from this population, I found in this sample from population 1, 140 students in that sample. That's why 140 out of 550. This is regarded now as P hat 1, our sample proportion from population 1. So subscript 1 is to indicate that the value came out from population 1. Calculation in decimal quickly came out to be 0.2545. And again, I stay in my usual decision to round these sample proportion values to 4 decimal places, unless being specified otherwise. But I leave that for viewers and students of mine to watch for your own rounding requirements anytime you're looking at different problems. So my p hat here, my p hat 1 is in decimal 0.2545. And now let's look over to the information given regarding population 2. So in the description on the computer screen, from Gauss University, we sampled 500 students. And so 500 students here now is being the sample size and supposedly N2. And within this sample, 100 students in this sample are in engineering majors. So immediately now from population 2, any sample size from population 2 is being as large as 500. And so in that way, the sample proportion that we have found, now I have to call that p hat 2, found to be 100 out of 500. But again, this is only a sample proportion. It came out from population 2, so it gets that subscript 2. And in decimal, this is 0.2 exact. And so a couple things to notice before I advance any further. But unlike the example that I offer throughout the general discussion, the general understanding of comparing two population proportions, this problem here shows us that we have different sample sizes, N1 and N2. And so that once again enforces the understanding that the sample size N1 is not required to equal the sample size N2. And in this way, we are clearly working with independent samples. The two samples we're looking at here are intended to be independent samples. And so now, in this way, how we have successfully listed down our given information, then further, we need to recall from the general lecture that dP as the difference from in the two population proportions is permanently defined as P1 minus P2. And as I said, permanently means this difference here is always the value from population 1 minus the value from population 2 for whoever that can take the role of P1 and whoever else can take the role of P2. So this is the difference in the two population proportions. And as a reminder, this value has only one unique value. And right from here, right from what we're doing, and especially when we have start seeing samples from the two populations, we must start thinking about any sample from population 1 can make a difference with a sample from population 2. So there we define for ourselves a dP hat defined permanently as a sample or any sample from population 1 minus a sample proportion value from population 2. And again, it is permanent definition in a sense that we always want the sample from population 1 to be before the subtraction sign, and the sample proportion from population 2 is to be after the subtraction sign. And so that's how, as we recall from the general lecture, this is how we define a dP hat value, a sampling difference. And so in that case, again, consequently, for this dP hat, there are unlimited number of values. And that's the reason why now we can consequently think of this dP hat as a random variable. It's a continuous random variable. So RV stands for random variable. And so now, before I start getting into question A right here, sooner or later we are going to need to use the actual difference in the two samples that we already had. So dP hats right from our two samples here, which is only one value among infinitely many of these dP hat values. So our dP hat here is 0.2545 minus 0.2, the difference between these two values. And again, this is a P hat from population 1 minus a P hat that we have found from population 2. And calculation here can quickly give us a positive 0.0545. And so under this decision, in this decision of mine regarding the numerical labeling of the two populations, then consequently our dP hat value turned out to be a positive value. But for any viewers who decide to give the numerical labeling the other way around, then consequently this dp hat would turn out a negative. So once again, it all depends on how you decide, on how I decide, or how you decide your numerical labeling. But once you have decided that, stay in these two definitions must stay in the exact same way right here. And then consequently, it can lead to negative or positive differences depending on how we decide the labeling convention here. But so back to this particular problem, this is a positive difference in the way, in my decision of labeling these two populations. And then eventually I am going to need to use the combined sample proportion from the two sample proportions here for my later work. So I am going to spend a little bit of time. Unlike the example I went through in the general lecture, here I can usually, when it gets to doing as a practical work, I always nail down all of the information regarding the two samples first, and then we're gonna take all that information as information that we have prepared ahead of time before we get into the actual doing the problem. So p hat c here, as a recall for yourself, the successive count from population 1, the successive count for engineering major, that category. So x1 plus x2, so successive count from population 1 is to be totaled up with the successive count from population 2. And we divide by the total of the two sample sizes together. So that's why we're looking at x1 plus x2 over n1 plus n2. And now with the actual values successfully plugged in, we're looking at 140 to be totaled up with 100, and all of that is divided by 550 totaled up with 500 in the denominator. So our combined sample proportion here turns out to be 240 out of 1050. And this is 0.2286 in 4 decimal places as a decimal value. And again, throughout all of my video lectures regarding comparison of the two population proportions, then I will stay with p hat c to be 4 decimal places. But it is the responsibilities for any viewer or any students of mine to watch for your own rounding requirements when it comes to doing these problems. So now that we have had p hat c and we have had the value for our particular dp hat here. And so now getting into the actual part A of our question, of our current problem or our current example here, then let's look at the wording as following. At given significant level alpha equals 0.001 are the samples showing strong evidence that proportion of engineering majors in Newton University is other than that in Gauss University. So here in this particular question itself, in this particular problem here, the wording is making it quite obvious. We want to compare the proportion of engineering majors in Newton University, and we want to prove the fact that this proportion from that proportion of engineering majors from Newton University is other than that in Gauss University. So it is quite obvious that we are trying to prove, according to the wording of the statements, we are trying to prove that P, but now P1, because this is the proportion of engineering majors in Newton University. We want to prove that this is other than that same population proportion, but in Gauss University. So it's P2, that's how we call it. And so now right from this comparison statement, algebraically we can rewrite that as P1 minus P2 as a difference between P1 and P2. And that difference there is to be stated as difference from 0. Or we can also rewrite algebraically that same comparison statement as P2 minus P1 to be different from 0 as a difference between P2 and P1. However, in our definition of dp that we have already defined, we permanently define dp as the difference p1 minus p2. So in this reasoning, I am going to choose to work with this particular statement right here, even though they are both algebraically correct, as in being the correct re-expression of this comparison statement. And the reason I chose this, because now I notice that p1 minus p2, this expression here is the same as our dp, which is consistent with how we define our dp. So in that way, looking at this, it looks like we have a statement. The question in our problem states the following: dp is other than 0. And so this is how the wording from the statement led to this final statement right here. And now, so as first step in testing a hypothesis, we need to identify our two hypotheses, H0 and H1. And as usual, H1 is always the easier one to find. So in this case, I have just now written it. So here our H1, the alternative hypothesis, says dp, we are trying to prove that dp is other than 0. And now once we have successfully identified our H1, the alternative hypothesis, H sub 0 will come out as easy as writing dp is equal to 0. So the null hypothesis is almost identical to the alternative hypothesis, except for the inequality is always changed to the equal sign here in our null hypothesis. And so further, this problem, in the way how this inequality sign is involved in our alternative hypothesis, we must run this test as a two-tail test. We must perform this test or proceed with this test as a two-tail test. And so now, starting at this step here, I am going to pick up the pace here, because I believe many explanations, many detailed explanations about the steps have been given in my general lecture, where I introduced a general understanding about the testing hypothesis that compare to population proportions. And so now we are ready for getting into the steps to perform our testing hypothesis problem here. So before we get started and writing down the steps, the formal steps for testing these hypotheses is right here. I gotta be clear that the earlier work that I have listed down, the information regarding population 1 and population 2 and sample 1, sample 2, is indeed not a required work. And further, the style, how I organize that into a careful table, as you have seen, is not necessarily required. So my point now is that in case anyone did not approach that way by listing down the information ahead of time, even though it was recommended, you can always spend a step calculating out dp hat here, right here in our formal steps. And so now, since I already had the value calculated earlier and listed, here I'm just simply going to rewrite the value here. So our dp hat value was calculated as 0.0545. So again, I'm saying that in case anyone did not approach the problem in a way that organizing out all of the information separately in a separate step, like how I did earlier, then you can always spend some time doing the calculation for dp hat and put it right here among our steps. And further, we can also spend some time calculating out our own p hat c value and put it here in our steps. And since I already had it calculated, I'm just simply going to rewrite it here. So our p hat c value earlier was calculated as 0.2286. And so now, after this step of getting our dp hat value and our p hat c value, now I am going to I'm going to go ahead and calculate the approximates for our sigma dp hat. So that approximates there can be done by, and again, let me remind the formula for anyone watching this video lesson here. We need p hat c times 1 minus p hat c, and multiply that product with 1 over N1, the sample size from sample 1, plus 1 over N2, the sample size from population from the sample 2, and we take the entire product there in a square root. And so now proceeding further into this calculation, it's just a matter of substituting in the value of PSC that we have already calculated earlier. So here I'm looking at 0.2286, substitute it in, multiply with 1 minus 0.2286, multiply with now our sample size N1 from the information that I've listed earlier. That was 550 for sample 1 from population 1. And the sample size that I have picked from population 2 was 500. So now what I have here is 1 over 550 plus 1 over 500. And so when we're doing this with a calculator, make sure to type it in this order right here, that we finish out the product. And then we're going to take the final answer inside the final answer of that product inside the square root. So I wrote it down here with a certain order of operations so that anyone can follow along, can also catch that way of how we run that on the calculator. Now calculation of mine came out for this approximate of sigma dp hat being 0.0259. So the actual calculation came out a lot longer for this approximate of the sigma dp hat. But in this video lesson here, allow me to use 4 decimal places. But be sure to watch out for your own rounding requirements when it comes to sigma dp hats in any of your testing hypothesis problems. And now that we have had the approximate value for sigma dp hat, we can now imagine that our sample dp hat here, our sample value being a dp hat here at this value 0.0545, is not the only sample being the difference between any two sample proportions. As a matter of fact, this value we have is only one among infinitely many others. And so we can imagine that all of those dp hat values can be placed on a bell curve. And any value on this line right here is a value that we can possibly find for a dp hat. So my point now is that we can generally regard a random variable for any value found on this line right here. The center of this bell curve is at 0, the value that is claimed in our null hypothesis. And this bell curve further has a sigma dp hat value, which we can only approximate that value by 0.0259 that we have calculated previously. So 0.0259 it is admittedly not the true precise value of sigma dp hat, but it's good enough that many generations of statisticians have been using it as an approximate to sigma dp hat value, which is the average spread of all dp hat values on this bell curve. So now in that way, our actual dp hat, our sample here as a dp hat value currently being 0.0545, can be found somewhere to the right hand side of this bell curve right there, to the right hand side of the bell curve center. So in that way, once we know that our bell curve here has an approximate for sigma dp hat, it has a center, and we know where we can find our dp hat, our particular dp hat value, we can now advance to the next step to calculate the z-score for our dp hat value. So we're finding z-score for dp hat by taking the difference between our particular dp hat value, 0.0545 and 0. So this 0 here is a value that's stated in the null hypothesis. The difference there is divided by 0.0259. And again, as a reminder, this is the approximate the value that we treat as the approximates for sigma dp hat. And so now we are calculating z-score for our sample as a dp hat value. Calculation of mine came out being positive 2.1 and allowed me to indicate the sign of our z-score for this sample in red ink right here. And so now, upon successfully calculating our z-score for the sample, we are now ready to advance to the next step, where we're going to calculate the p-value for our sample here. So setting up the calculation for our p-value is done as following. We are going to set up the probability calculation that on this bell curve, we are going to find a sample value being a dp hat greater than or equal to 0.0545. And so now at this point right here, I have not even completed my setup for the p-value calculation, but allow me to take a quick pause right here to point out a couple checkpoints for consistency. So what we can check for consistency here is that the z-score that we have had here being a positive z-score must be consistent with this setup here for the probability calculation being using a right tail inequality, an inequality that points to the right hand side. So in here I'm writing that sample dp hat value greater than or equal to 0.0545 to be consistent with that 2.1 right there. And just like that, having a z-score being positive, it should be consistent with the fact that our sample is found somewhere to the right hand side. And now in the end, this probability setup here is only, and this probability calculation setup here can be understood as the area on this bell curve that is shaded to the right hand side of our sample. That's how we understood that graphically on this bell curve. And so currently we're setting up the probability calculation as a right tail, and that's how I set that earlier. But in the end, this statement by itself is only indicating how we run a test as a right tail test. But indeed, our test here from the beginning was already concluded to be a two-tail test. So in order to calculate the precise two-tail p-value, this probability must be double or multiplied by 2. Multiplying that probability by 2 here can be understood the same as on this bell curve. We can imagine that there's another area exactly symmetric from this area but points to the left hand side. And so doubling this probability to calculate the p-value here is the same as calculating the total area, the total shaded area on the two tails right there. And that's why the test here, once again, is called a two-tail test. And so now that's our complete setup of the p-value calculation. And so now to get further into calculating this final p-value, this probability calculation is equal to the probability that on the standard normal distribution bell curve, we're looking for a z-score greater than or equal to positive 2.1. And that is the reason why I always want my students to calculate z-score before we get into calculating the p-value, because that's where we need it. And this probability will be multiplied by 2. And now we are going to calculate this probability by firing up our NormalCDF command on the TI-83 or 84 calculator that I am using. And so now on my TI-84 calculator here that I'm using, we can call the NormalCDF command by pressing the key combination second variables, which will bring up all of the distribution functions for statistics. We're going to look for normal CDF under option 2. I'm going to press enter. And so what we see here is a menu. But for TI-83 calculators or many early TI-84 calculators, after calling the normal CDF command, instead of seeing the menu as you have seen earlier, you will see the normal CDF command being printed directly on screen with an opening parentheses here. So this is where we have to manually input our values to complete the command. And so now back to the calculator that I was using, the version of the TI-84 calculator that I was using here. We're going to enter lower and upper for our interval here. And so one more time on the board right here, this interval of z-score we're calculating, or the interval that we're shading here, has a definite low end but an indefinite upper end, where this lower end here is equivalent to z-score positive 2.1, and we have again an indefinite upper end. So in that way, for low end here on the calculator, I'm going to enter positive 2.1. For upper end, I am going to enter 1E99. And since we're running this normal CDF command on the standard normal distribution, we will default mu and sigma to 0 and 1. And I am going to hit enter a few more times. So for any TI-83 or early TI-84 users, this is how you will complete the normal CDF command manually after the command was printed directly on your home screen right here. Low end comes right after the parentheses, then a comma, then the upper end, then a comma, 0, comma 1. And we close the command with the closing parentheses. And now for all versions of the TI-83 or 84 calculator, we are going to hit the final enter to obtain our final result right here. So this value here came out being 0.01786 and a lot longer. And so just that probability here, again, as I have explained, to calculate that, we ran the normal CDF command. And so allow me to spend a minute here to finish, to complete the command for that program. 2.1 positive 1E99, comma 0, comma 1. But don't forget, we need to multiply whichever comes out from running the normal CDF command by 2, according to the work that was previously set up here. And so that means in our next step, we have found this answer that came out from normal CDF command will be multiplied by 2. So 0.01786 for 3 and a lot longer. Now, I always leave this value here without rounding until the very last step where we have the final answer. That's where I round if I have to. And so now this probability here must be multiplied by 2. Final calculation came out for our p-value being 0.0357. And so this is usually in my style, this is where I can put in some rounding. And so normally I round to 4 decimal places, but be sure to watch for your own rounding requirements anytime you're doing these problems out there. So this is our p-value. Now that we have had our p-value successfully calculated as a two-tail p-value for this two-tail test, the next step now is to compare this with the significance level given in the problem. So now back to the wording on the problem right here. It says at significance level 0.001. So this is apparently our given significance level in a problem. And so that means our final two-tail p-value here compared to the significance level indicated earlier is above or greater than the significance level 0.001 as given in the problem. And so upon realizing that our final p-value stays above the significance level, we lead to the following conclusion, that our sample as a dp hat value is not an unlikely sample, or for short, it's not unlikely. And what it means is that nothing unlikely about our sample being a dp hat. That further means, as a conclusion, our sample as a dp hat value is not showing strong evidence, or itself not strong evidence. For us, on one hand, to either say to reject h sub 0, or we can say that dp hat is not strong evidence for us to support h1. Now, so in this way, another way of arguing is that our dp hat, according to the p-value that we have observed here in our calculation, which came out being above the significance level, it means our p hat here, our dp hat here, as an evidence, our dp hat fail, or we fail to reject h sub 0, with this dp hat being our evidence. Or alternatively, we can say we fail to support h1 using this sample as a dp hat value by observing that our final p-value calculated here came out above the significance level. And now ultimately back to the wording of the question itself. Again, I have to clarify that the question here for any testing hypothesis problem is a yes or no question. As it's stated here, are the samples showing strong evidence? So it's looking for yes if we had strong evidence, or no as the answer if we didn't have strong evidence. And apparently we did not have strong evidence. dp hat did not show strong evidence for us. So ultimately the answer to this overall question is no. dp hat did not show strong evidence for us to reject h sub 0 or to support h1. Or another way of saying, we fail to reject h sub 0 or we fail to support h1. And here we have arrived at our part B of the current example. So it is the exact same description of the two samples here. We've had 550 students sample from Newton University, where inside of that sample we found 140 of them are in engineering majors. And similarly, we sample 500 students from Gauss University, where we found 100 of them in that sample are in engineering majors. And so from the given information regarding the two samples here, we have already found for ourselves that dp hats, our sampling difference in the two sample proportions, calculated as p hat 1 minus p hat 2, and that value was 0.0545. So we already had for ourselves, and this is we calling this our sample value right here. And so now for the problem itself, question in part B asks us to construct a 99.9% confidence interval, and we want for estimating dp, the difference, that unique difference in the two population proportion values. What we're working with here in part B of our current example is a confidence interval problem. then allow me again to remind that anytime we're constructing a confidence interval or we're finding a confidence interval, then all we need is to obtain a sample value. And so any sample value is either given or purposely obtained by ourselves by using any of the sampling techniques. Then from the sample value that we have had, we are going to add and subtract a margin of error to that sample value. And that's how we come up with our final confidence interval. And so, and again, the confidence interval is to estimate a value, a population value. So back to the wording of the problem, we want to estimate dp as the population value. So in that way, it means the sample we use here have to be the corresponding dp hats. And so now our final confidence interval must formally be in a form of, from where our sample value dp hat is, we are going to add and subtract the margin of error from that. And then just earlier I brought up the sampling information that we have already calculated, or in other words, the value, the actual calculated value for dp hats that we're currently having. And that value was 0.0545. So that means our final confidence interval must be in a form of a margin of error added to or subtracted from 0.0545. And so ultimately what we need here is to calculate this margin of error. And so the margin of error, as we have learned back in the general lecture, together with the example given there, along the way there, then we know that margin of error must be done by z sub c multiplied with the square root. And inside the square root, we have p hat 1 multiplied with 1 minus p hat 1 and divide that by sample size n1 plus p hat 2 in product with 1 minus p hat 2 and divided by sample size n2, and all of that lengthy expression is taken inside of a square root, and the square root expression here is multiplied with z sub c. And let's one more time have a look at our given sampling information. So our sample p hat 1 is in decimal value 0.2545, where our sample p hat 2 in decimal value is 0.2. The sample size we used for all samples in population 1, or in other words N1, was 550. And the sample size that we used for all sample proportions from population 2 was 500, or in other words N2 equals 500. So in that way, now we realize that our margin of error formula is almost completed, except for the value for z-score. So now let me go ahead and plug in all the values for p hat 1, p hat 2, n1, and n2. 0.2545 for p hat 1 times 1 minus 0.2545 for p hat 1, and divided that product there by 550. And this entire expression is inside the square root. And still inside that square root, I am going to add with another expression, 0.2, as for my p hat 2 times 1 minus 0.2, and I'm dividing that expression there by 500, the sample size n2. So two separate fractions, two separate expressions being added inside of this lengthy square root. And so now we won't be able to proceed any further unless we find the value for z sub c. And so many explanations were given in the general lecture with the example given along the way there. So here I'm just going to quickly speed up through the process of finding z sub c. So to find z sub c here, first thing to recall that our confidence level is given as 99.9%. So that is 0.999 in decimal, because That value is given here. The question is asking us to construct a 99.9% confidence interval. So this 99.9% is our confidence level given in the problem. So in that way, now having our confidence level given and expressed now as a decimal, step 1 is to proceed as 0.5 plus half of my confidence level. Calculation of mine came out to be 0.9995. And again, just like any other finding z sub c problem, I'm going to regard the answer of this step 1 here as the left area, or some technology refer to this as the area left. Step 2, our final z sub c value will be calculated by running a technology that will invert this left area calculated from step 1, and so to come back with a z-score. And so I have developed my own INVZ program. There are many other programs over the web that does the same thing. Again, what this program will do is to find what z-score has this area shaded to the left, or in another way of saying, this program will invert this area as a left area to find out what z-score that is, having this area shaded cumulatively to the left. And so when the program is asking for the area left, the only value it's asking for, then I'm going to enter a 0.9995. And so now for anyone who is using a TI-83 or 84 calculator, we can find a program equivalent to the INVZ program by pressing the key combination second variables. That will bring up all of the distribution functions for statistics. So the program equivalent to the INVZ program is called the INV norm on the TI-83 or 84 calculator. And so now I'm going to select that option that says INV norm and hit enter. So this particular version of my calculator, of my TI-84 calculator, shows the INV norm program as a menu where it's asking for area. So this is equivalent to the left area that you have seen on the writing board earlier. But be careful that when you are running a TI-83 or some earlier TI-84 calculators, after calling the INV norm program, instead of seeing the menu as seen earlier, the INV norm program will print a command INV norm with an opening parentheses right on your home screen right here. So for users of the TI-83 or early TI-84 calculators, you must type in all of the values manually to complete your INV norm command. And so now back on the version of the TI-84 that I was using initially, for this area here of the INV norm program, I am going to enter the value 0.9995 as we have seen earlier on the writing board. Now we're going to hit an enter, and we will default, and we will always default these values mu and sigma to 0 and 1. So I'm going to hit enter a few more times. And so if you're on a TI-83 or earlier TI-84 calculators, this will be the way how you enter your values. So the left area that you have seen on the writing board earlier is entered here right after the opening parentheses. Then comma with 0 for mu and 1 and with a comma and 1 for sigma, and we close the command with a closing parentheses. And now for all versions of the TI-83 or 84 calculators, we are going to hit a final enter to obtain our z sub c value. And so this is the z sub c value for here. And for anyone who is not using the TI-83 or 84 calculator, you can either find an equivalent technology that can do the similar functionality, or you can use the INVZ program that I have developed to run with Microsoft Excel here. And this program is given out for free for students who are taking classes with me. So in this box that's labeled left area, this is where I'm entering 0.9995 as this is the area to the left of our z-score that we are finding. Then hit enter to execute it. So now notice that this value here has changed. So this is the final z sub c value, and it's a quite lengthy value. So again, unless being specified otherwise, for all of my z sub c values throughout my video lectures, I will be using 3 decimal places. However, again, that is the responsibility of viewers and my students to watch for the rounding requirements in every single problem that works with the z sub c value. So here my z sub c is concluded to be, even though a very lengthy value, but now in 3 decimals, 0.291. And so now after successfully finding the value for z sub c, our margin of error formula is ready for the final calculation. So as a calculation, it is 3.291 to be substituted for z sub c, and the rest of the expression will be square root expression of 0.2545 in product with 1 minus 0.2545 divided by sample size 550. And still, inside the square root, I'm going to add with another expression, 0.2 times 1 minus 0.2 divided by 500. So my final calculation came out to be 0.084864 and a lot longer. And for this specific problem right here, allowed me to round to 4 decimal places. And again, I leave that as a responsibility for viewers and students to watch for your own rounding for the margin of error anytime you work with this kind of problem right here. So here in my problem, I am going to round to 3 decimals, 4 decimals, 0.0849. So that now means our final confidence interval is ready. From 0.0545, which is our sampling difference in the 2 sample proportions, or generally our sample value right here, we are going to add and subtract 0.0849. And that is how we come up with this confidence interval. And so the actual difference in the 2 population proportion values is expected to be inside of this interval, confidence at 99.9%. And again, we can always put this confidence interval in traditional format by simply subtracting this margin of error from the center point or adding this margin of error to the center point. So low end would be minus 0.0304. And high end will be 0.1394. And so this is the same confidence interval but expressed in traditional format. And again, at 99.9% confidence level, or at 99.9% successful level guaranteed here, then our dP value will be somewhere inside of this interval between the low and the high here at 99.9%. And so for any of my students, I expect that you are flexible with understanding both of these 2 formats of our final confidence interval, any of our final confidence intervals. And so before we are completely finished with our current problem here as a separate example from the general lecture. Then let me make a couple of final remarks here, connecting the results from part A that we have done previously and part B that we have just done now. So in part A, we were doing a testing hypothesis problem. And so let's look at how our hypothesis is again. H sub 0, and of course, according to our labeling convention for population 1 and population 2, then we came to our null hypothesis stating that dp was equal to 0. And alternative hypothesis was arguing otherwise. dp was other than 0. And we started out by accepting h sub 0. But in the end, we actually failed to reject h sub 0, meaning there's nothing wrong with accepting this null hypothesis, or there is still some likeliness, a likeliness somehow that dp can still be equal to 0. And so now let's look at the result we have found for our confidence interval. And in this case right here, it is best to look at the interval in traditional format. And that's why I highly recommend that any of my students can understand the interval in two different formats interchangeably. But the confidence interval of ours that we have found in traditional format looks as following: minus 0.0304 to be the low, and 0.1394 is the high. So look at this interval over here. Low end is going somewhere into the negative side, and the high end is somewhere on the positive. So think about the lineup number over here. If 0 is a value somewhere on this lineup number, then the lower end of our interval is on the negative side, negative 0.0304. And admittedly, the high end stays further away from 0. And the high end was a positive. So now looking at the picture, it makes a perfect connection with the result we have found, because we have already failed to reject h sub 0, stating that dp would equal to 0. And failing to reject this means, look at this right now. The 0 value is still contained completely inside of this interval. And dp is guaranteed at 99.9% confidence level to be inside of this interval. So that's the reason why it's just to be consistent with the result from part A. dp can still have a likeliness to equal exactly 0.